Phony-C is based on the concept of vulnerabilities modules. Vulnerability modules is a concept really similar to what Nepenthes and then Dionea. The concept is the same because everything is developed as a separate module. So we have the core browser functionalities, which are developed separately from the browser plugins, emulation, and the ActiveX controls. In particular, you can read about the mock ActiveX control. The mock ActiveX control is used when there is no implementation of the emulation of a particular ActiveX control, and so a generic one is instantiated in order to understand what is going on. Another important piece of Phony-C is related to shellcode detection and emulation. In here we have two ways for detecting it. Sorry. The first one is Honey.js, I told you about before. Honey.js uses a really simple but effective approach for detecting heap-sprying exploits. In particular, it uses this approach. It analyzes the operation, the assignment operation while executing the JavaScript code, and in particular when there is an assignment operation, it interrupts the engine and tries to understand what's going on, so understanding if there is effectively an attempt to spry the heap. Honey.js was written, think about it as a modification of the SpiderMonkey engine. And then there is another way to detect the presence of a shellcode to the integration of libemu. Other presentation during the morning talked about libemu, and in particular in Phony-C we use such code for shellcode detection, execution, and profiling. These are the future improvements. What I'm currently working on. It's too early for talking about results because I'm at a really an early stage about such improvement. First of all, a new and more reliable document object model emulation. Currently, I've coded the code emulation which is fully compliant with level 1 W3C specification. You have to know that modern browsers are all fully compliant with level 1 specification, partially compliant with level 2, and some is introducing level 3 functionalities. In particular, as I said before, this first point is really important. A precise DOM emulation means the possibility to detect more and more attacks, even those even 0 days attacks. The second important point is replacing SpiderMonkey with Google V8. I must confess that I'm starting hating SpiderMonkey because it is absolutely unfeasible. You cannot extend it, you cannot wrap into it in an easy way. There is no API, no real API. So I'm turning to Google V8, which is on the other side. It is really cool in its design, it's well-documented APIs. In particular, it gives to you the possibility to use a debugger or an abstract syntax tree compiler. And this is really useful for the third point, because I would like to make the analysis. Right now, Phony-C works just on a dynamic analysis for detecting potential attacks. My idea is to turn it into a mixed approach, so using even a static analysis, starting from the abstract syntax tree of the JavaScript code, in order to have a much more reliable, much more precise detection process. These are the ideas for the future, but as I said before, it's really too early for talking about results because I started just a few months ago.
So I'll talk about high interaction honey clients or client honeypots. As Angelo said, the low interaction client honeypots like PhonyC are emulated clients. High interaction client honeypots are real clients. So think Internet Explorer 6 on XP. That is still one of the most attacked platforms. With the real system, then you have the opportunity to use different ways of detecting attacks. And what this allows you to do is detect the effects of a successful attack, which is a little bit more difficult to do on a low interaction honey client. And the way that works, you have usually a set of client honeypots. High interaction client honeypots are rather slow and resource intensive, so you need a lot of them in order to crawl the web. And then you have a list of URLs that you feed into that system. And then the client honeypot just makes requests to each server and consumes and processes the response, maybe displays the page. And while it's doing that, it's monitoring the system for any unauthorized state changes. So if, for instance, in this particular instance, you don't detect any state changes, so you move on to the next URL, send a request. Now the server is responding with an attack that exploits the browser or one of the plugins, and then it places a new file in the startup folder. Now, since nothing else was going on the system, you know that the URL that you just crawled is responsible for that state change on the system, and you can conclude that that URL was just malicious. Similar to low interaction, high interactions have some strengths and weaknesses. Well, first of all, there's no emulation necessary. Once you have a browser on a vulnerable system, well, that's basically your simple client honeypot. So it's kind of quick to get going. It's very accurate in classifying URLs. If you see a new file appear in the startup folder, well, the likelihood of false positives is very low. And because you're not using any signatures in the underlying system, the high interaction client honeypots are capable to detect zero-day attacks. So attacks that you don't know about yet. And because you're dealing with a real system, it's much more difficult to evade. It's harder for the attacker to fingerprint the system to find out whether you're dealing with a client honeypot that is automated, so that crawls the web, or a real user that uses IE6 to just browse the web. But as Angelo mentioned earlier, they're a little bit more dangerous because now you're using the vulnerable system. It gets actively attacked. The shellcode executes, the malware is being pushed and downloaded and executed. And because they're a little bit more resource intensive, usually they're deployed as part of a set of virtual machines. You need a lot of computing power. And they tend to miss attacks because you need to have the vulnerable system match the attack. So if you run Firefox and you go into crawl a web page that attacks Internet Explorer, you will not be able to see the effects of the successful attack, and therefore you will miss it. A high interaction client honeypot that I've developed with a bunch of folks down in New Zealand during my PhD studies is Capture HPC. The latest version is 2.5. Basically, it's a set of virtual machines that are being driven by a server component to crawl and analyze URLs. It's very flexible around the client application that it uses to crawl the web. So you can use IE, you can use Firefox, you can use Safari, but you can also span into non-browser client application. Think about Adobe Acrobat Reader. You can configure Capture to just open PDF documents one after another. And if a PDF document is malicious, well then Capture is able to detect that. It's forensically ready in that it records information on the vulnerable system at a very low level. It records it at the kernel level, so it's very difficult for the attacker to kind of fool that detection mechanism. It collects all the malware that is pushed onto the system, as well as the network traffic. So later on, you can go back and analyze basically those collected files. and it's currently maintained by the New Zealand Honeynet project chapter. So that is Capture HPC and high interaction client honeypots. But what I want to talk about most is malware distribution networks. So malware distribution networks, it's a set of web servers controlled by a group of cyber criminals to distribute malware efficiently. What we've been talking so far is in terms of URLs, and we're saying a URL is malicious. But what turns out to happen is the URL is just a legitimate URL. It's on a legitimate web server, and they're usually hacked by a third party that manipulates the web page to join it into a malware distribution network to pull in additional code from servers that are under the control of the attacker. So these are specialized structures, these web servers, are arranged in a way that supports specialized roles for the cyber criminal. So in the underground market, you may say to somebody who controls like a redirector, send traffic to my server, I have the latest zero-day exploit and I want to push this malware. And then basically that malware distribution network is temporarily rented out to me to distribute my malware. And it allows to run campaigns. So this is how this malware distribution network looks like. This is taken from a Microsoft report that we publish annually. So you have your user that maybe uses a search engine, Bing, to search for a specific web page. The user then clicks on that web page, and the web page renders within the browser. Now that web page may be infected with, by a malware distribution network that pulls in an iframe from another server that is under the control of the attacker. Now that code runs again in your browser and maybe fingerprints your browser. It assesses what country are you in, what plugins do you have installed, what version of browser are you running. And then once it determines that, it redirects you yet to another server that then has exactly the exploit that works on your machine. That exploit then takes control of your machine and then maybe downloads malware yet from another machine. So that's kind of the concept of malware distribution networks and how they're structured. Now at Bing, of course, we're crawling the web with thousands of machines and therefore have a lot of data that we're able to analyze. So we have a little bit more insight on how these malware distribution networks are structured. So if you think about that the red circle here in the middle is a malware distribution network, and the gray circle is a landing page that has been hacked, a legitimate server. Usually you see structures like this, where thousands of landing pages point to one malware distribution network. So for us, it's very important to detect and understand that malware distribution network. And this is another slide that kind of shows the information in a little bit of a different way. So here, what we're seeing is the reach of one malware distribution network. So all the way on the left here, we're seeing malware distribution networks that are pointed to like 700,000 pages. And then it quickly drops off and goes into a long tail. So we can say that a minority of malware distribution networks is responsible for the majority of hacked landing pages. So that's malware distribution networks. Now let me kind of jump into challenges and future work. And I continue to talk about malware distribution networks because there are some challenges in the way they're structured. So let's assume we have two malware distribution networks. They're depicted here. So the black line shows the number of landing pages that we detect that point to that one malware distribution network. So it's about 4,000 landing pages. And it stays pretty constant. They just kind of exist for a long time frame. But then in 2009, we started to detect malware distribution networks that rapidly appear, infect a lot of sites, infect a lot of end users, and then just disappear.